So now let's talk about the rules of the S-DOD. And these are going to be very, very similar to the central limit theorem, as you'll see. So first thing is this. If the S-DOM for x and the S-DOM for y are both normal, then the S-DOD is going to be normal too. And so think about when these are normal. These are normal if your population is normal, right? That's one case where it's normal. These are also normal when n is large, right? So in certain cases, you could assume that the S-DOM is normal. And if both of these hold up to, have met those conditions, then you could assume that the S-DOD is normal too. Great. So shape. We have conditions where we can assume it's normal, and they're not crazy. They're things we've learned before, so cool. What about the mean, right? Because it's always shape, center, spread, right? What about the mean for the S-DOD, sorry. The mean for the S-DOD, right? That's going to be characterized by mu sub x bar minus y bar, right? That's the idea, right? Now let's consider the null hypothesis. In the null hypothesis, usually the idea is they're not different. Like nothing stands out. So y doesn't stand out from x. X doesn't stand out from y. And that really means we're saying they're very, very similar, right? If that is the case, what we're really saying is that the mean of, when we take x bar minus y bar and do it over and over again, on average, the difference should be 0, right? Because what we're really saying is, hey, sometimes the difference will be positive, sometimes the difference will be negative, but if x and y are roughly the same, right, then we should actually get a difference of 0 on average, right? So for the null hypothesis, this will be 0. That's the null hypothesis. So what would be the alternative hypothesis? Something like the mean of the S-DOD is not 0. Right? So this is in the case where x and y assumed to be same. Right? Because that's always what the null hypothesis is. They're assumed to be the same. They're not significantly different from each other. Okay, so that's the mean of the S-DOD. Now, what about standard error? Well, first of all, in order to calculate standard error, you're going to have to know whether these are independent samples or not. So remember, if you go back to sampling, independent samples is where you know that these two come from different populations, and picking one doesn't change the probabilities of picking the other, right? So as long as these are independent samples, then you could use these ideas of standard error. So as we said before, for me, it's easier when I think about the variance of the S-DOD first, because that rule is quite easy. So the variance of S-DOD, so the variance is going to be just the variance of the S-DOM of one guy plus the variance of the S-DOM for the other guy. Right? Notice that these are the x bars and the y bars, right? So these are really for the S-DOMs. They're not for the populations nor the samples. Okay. And then from here, what you could do is sort of just derive the standard error formula, right? Because we could just square root both sides, right? And so if you wanted to just get standard error, then it would just be the square root of adding each of these variances together. But let's say you double click on this guy, right? What's inside of him? He's like a stand-in for just the more detailed idea of S, right? Squared sub x, right, over n sub x, right? Because remember, when we talk about standard error, we're talking about standard error is equal to s over the square root of n, right? So the variance of the SDOM is equal to s squared over n, right? And so if you imagine squaring this, you would get s over square root of n, right? But we need the variance, so that's why we put variance here. And you need to add the variances together before you square root them. And so here we have the variance of y over n sub y, right? And so you could write it either like this or like this. They mean the same thing. They're perfectly equivalent. You do have to remember that addition goes before. So when you have this all under the square root sign, the square root sign acts like a parentheses. So you have to do all of this before you square root, right? Order of operations. Okay. So that's standard error. I know it looks a little complicated, but it really isn't. They're just all the principles we learned before, but now we have to remember, does it come from x or does it come from the y distributions, right? So that's one of the few things you have to sort of ask yourself whenever we deal with two samples. Okay. So now that we know the sort of revised central limit theorem for the sampling distribution of the differences, now we need to ask, when can we construct a confidence interval for the difference between two means? And actually, these conditions are very similar to the conditions that must be met when we construct an SDOM, right? But there are a couple of differences because we're now dealing with two samples. Okay, so three conditions have to be met. All three of these have to be checked off, right? So one is independence. So the notion of independence. So the first is this. The two samples were randomly and independently selected from two different populations, right? So that's the first thing you have to meet before you could construct a confidence interval. The second thing is this. This is sort of the assumption for normality. How do we know that the S dot is normal? Well, it needs to be reasonable to assume that both populations that the samples come from, so the populations, are normal. Or your sample size is sufficiently large, right? So these are the same ones that apply to the central limit theorem, right? So this is the case when we can assume normality for the SDOM, but also the S dot, right? Okay, so in number 3, in the case of sample surveys, the population size should be at least 10 times larger than the sample size for each sample. And the only reason for this is that remember we talked before about replacement, sampling with replacement versus sampling not with replacement? Well, whenever you're doing a sample, you're technically not having replacement. But if your population is large enough, then this condition actually makes it so that you could assume that it works pretty much like with replacement, right? Because you have like so many people, it sort of doesn't matter. So that's the replacement rule. Okay, now finally we could get to actually finding the confidence interval. So here's the deal. With confidence interval, let's just review how we used to do it for one mean. So one mean confidence interval. So back in the day when we did one mean and life was nice, what we would do is often take, we would take the SDOM and assume that the X bar, the sample mean, is at the center of it. And then we'd construct this, whatever, usually something like 95% confidence interval, right? So these are 0.025, right? Because we have, if this is 95% and it's symmetrical, there's 5% left over, but it needs to be divided on both sides, right? So, and then what we did was we found these these boundary values, right, by using this idea. Plus, so this middle, plus or minus, plus will give you this side, minus will give you this side, plus or minus how many standard errors you are away, right? And that we used either t or z. Remember, I'm just going to use t from now on because usually we're not given the standard deviation of the population, right? Times the standard error, right? So that was our basic idea from before. And that would give us this value as well as this value. And then we could say we have 95% confidence that the population mean falls in between these boundaries, right? Okay, so that's for one mean. What about two means? Two means CI. Well, in this case, we're not going to be calculating using the SDOM anymore. We're going to use the SDOD, right? And you know, if this mean is going to be x bar, right, the sample mean, then you could probably assume that right here it might be something as simple as the difference between the two means, right? So that's what we assume to be the center of the SDOD, right? And then we, you know, just like before, we, you know, whatever level of confidence you need, 99%. If it's 99%, you have 1% left over on the sides. You have to divide that 1% in half. So 0.5% for this side, 0.5% for that side, right? But in this case, let's just keep it as, you know, we'll just keep the 95%, right? And what we need to do is find these borders, right? And what we could do is just use this exact same idea again. We could use that same idea because we could find the standard error of this distribution. We know what that is. And so let me write this out with sort of the right, instead of writing just standard error, because that's ambiguous, we'll write S sub x bar, right? And so here, we could actually just translate these ideas into something like this. That would be taking this, adding or subtracting how many jumps away you are, right? Like the distance you away. So that would be something like x bar minus y bar, right? Instead of just having x in the middle, we have this thing in the middle, right? So I'm just putting that in there. Plus or minus, the t remains the same, t distributions, right? But we're going to have to talk about how to find degrees of freedom for this guy, right? And now the new SE, right? But now this is the SE of the difference, right? How do we write that? Well, x bar minus y bar plus or minus the t times, and we can now write the s sub x bar minus y bar, right? And if we wanted to, we could, you know, take that all out into the square root of, you know, variance of the SDOM for x and variance plus SDOM for y added together, right? So we could unpack all of this if we need to. But this is the basic idea of the confidence interval of two means. Now, now, in order to do this, I want you to notice something. Here we need to find t, and because we need to find t, we need to find degrees of freedom. But not just any old degrees of freedom, because right now we have 2 degrees of freedom. Degrees of freedom for x and degrees of freedom for y, right? We need a degrees of freedom for the difference, right? That's what we really need. And so let's figure out how to do that. Okay,